Okay, so our mission today is really to unpack two pretty notorious types of attacks, command injection and SQL
Now,
injection.
what's really interesting, maybe a bit scary, is that both of them exploit a similar core weakness.
Hmm.
It's all about how software handles the data you give it.
Right. So we're not just talking theory, we're looking at real threats and, crucially, the practical ways developers and really anyone interested in security can defend against them. Okay, let's start with command injection. What exactly is that?
Okay, command injection.
Hmm.
Um, Fundamentally, it happens when an application takes data you've provided, user input, and uses it to run commands directly on the computer's operating system.
So the application kind of becomes an unwitting messenger for bad commands?
Pretty much, yeah. It acts as a channel for potentially harmful instructions.
The data and information lecture had a really clear example using CGI, which is a bit older now, but illustrates the point well.
Right. The scenario was a script designed to email a file. You'd give it a file name and an email address. This system might build a command like cat file name mail email address.
Okay, so cat shows the file. The pipe sends that output to the mail command. Seems straightforward. Where's the problem?
The problem is if a user puts something malicious in that email address field, like the example Eric at cs.rmrmrmsr.
Whoa, okay. Let's break that down. The pipe character is key here, isn't it?
It is. It tells the system, okay, take the output of the first command and use it as input for the next command. But because the user provided that second pipe and the RMAAF
The system just runs it. RM-F. What does that do again? I know it's bad.
it's very bad. It means remove forcefully and recursively everything starting from here. Basically, delete all the files it can access. So instead of mailing a file, the script ends up wiping out data.
That's terrifying. Like leaving your front door wide open with a note saying, help yourself. The lecture also mentioned a similar risk with C code, right? Using Sprint end system.
Exactly. A program might build a command string, maybe for printing, like LPR-P printer name, file name,
Yeah.
using sprintf to put the user's printer name in there.
Yeah.
Then it uses system to run that command.
And the vulnerability comes if the user enters something tricky as the printer name, like Muro, exterm.
Precisely. That semicolon acts as a command separator in many shells.
Ah, okay. So the system tries to run LPR SP Miro, finishes, and then just goes ahead and runs exterm as a completely separate command.
Yep. And exterm could open up a terminal window, potentially giving the attacker direct shell access. The lecture also mentioned the ampersand interad, which could run that exterm in the background, making it harder to spot immediately.
Wow. And it's important to realize this isn't just a C problem or an old CGI problem.
Not at all. The lecture pointed out examples across lots of languages. C++, Java using exec or runtime.exec, Perl with its backticks for running commands, even older Python versions using system or unwisely using input directly in commands. It's a widespread risk if you're not careful.
It really hammers home how easily user input can be misinterpreted as instructions. How does this tie into that CIA Triad concept from the security lecture PDF? Confidentiality, integrity, availability.
Good question. Command injection directly impacts availability. Think about it if an attacker injects a command like shutdown, as question 3 on that mock exam suggests.
The whole application or even the server could just, well, shut down, making it completely unavailable.
Exactly. So, okay, we know it's bad. What do we do about it? What are the defenses? Both sources had quite a bit to say here.
The absolute '1 defense seems to be input validation. Checking that user input very, very carefully.
That's the big one, yeah. As data in information.wave stressed, you must meticulously check any data coming from the user before you use it anywhere near a system command. Never ever trust user input by default.
Be inherently suspicious. Got it. And the second major principle was running with least privilege.
Absolutely. If your application only has the bare minimum permissions it needs to do its job, then even if an attacker does manage to inject a command, the amount of damage they can do is limited. It contains the blast radius, so to speak.
Okay, let's circle back to validation. The lecture talked about blacklisting versus whitelisting. Can we unpack that a bit more? Why is whitelisting considered so much better?
Sure. Blacklisting is where you try to define all the bad things. You say, okay, block semicolons, block pipes, block ampersands.
Sounds reasonable on the surface.
Well, the problem is, as both sources imply, it's practically impossible to think of every possible dangerous character or combination. Attackers are creative. You'll always be playing catch-up, trying to block the latest trick. It's just not robust.
Like a leaky sieve, you plug one hole, another appears.
Exactly. Whitelisting flips it around. You define only the good stuff. Say, for this username field, I will only accept letters A through Z, numbers 0 through 9, maybe an underscore, and it must be between 5 and 15 characters long.
Ah, so anything else is just rejected outright.
Right. You define a very strict set of allowed inputs. This dramatically reduces the potential attack surface because you're not trying to guess all the bad things. You're just enforcing what's known to be good. It's proactive, not reactive.
Makes sense. The lecture also mentioned encoding.
Yeah, encoding is about transforming potentially harmful characters into a safe form, like in HTML, how demand side becomes an elt. So the browser just displays it instead of treating it as a tag. You could do similar things for command inputs, but honestly, it gets complicated fast and it's easy to get wrong.
And the web security PDF really hammered home the idea of just avoiding running system commands with user input if you possibly can.
That's a really key point. If your programming language has a built-in function to do what you need, like manipulating files or network settings, use that. Don't shell out to the operating system command line if you can avoid it, especially with user data involved.
Less opportunity for things to go wrong.
Definitely. And the PDF gave that specific Java example using Process Builder, where you treat the user input as a single distinct argument, rather than just mashing strings together to feed into runtime.getRuntime.exec, which is way more dangerous.
Treat the whole input as one piece of data, not a potential string of commands, which ties perfectly into that mock exam question number 4 about the ping command, right?
Absolutely. The question was how you could use ping to read secret.txt. Inputs like example.com, catsecret.txt, or example.com and catsecret.txt work because the application just takes that whole string
Including the semicolon or the double ampersand.
and passes it to the system's command interpreter. The interpreter sees the odal, or an ninja, and says, okay, run ping example.com, then run catsecret.txt. The application was tricked into executing the second command.
Okay, that gives us a really solid picture of command injection. Let's switch gears now to the other major threat we wanted to cover, SQL injection.
Right, SQL injection or SQLine. This is where attackers sneak malicious SQL code into the queries an application sends to its database.
Usually through things like web forms or maybe parameters in the URL.
Exactly. Anywhere user input gets incorporated into a database query is a potential vector. And the core danger, as the Web Security Lecture 1.pdf points out, is that data provided by the user ends up being treated as executable code by the database itself.
Data becoming code again, it's a recurring theme.
It really is. The PDF uses a classic example, a vulnerable login form. The SQL query behind the scenes might look something like select name, grade from users, where email, and password.
So it's trying to find a user row where both the email and password match what was entered. What's the attack?
A very common basic attack is to enter something like 1 in the password field.
Okay. Or 1. How does that break the login?
Well, look at the where clause. The first single quote you enter closes the expected password string. So the SQL becomes and password L11. Now, 1 is always true. So the condition becomes password it or true. And anything or true is always true.
Ah, so the entire where clause effectively becomes where email or believe whatever mail and true, which means it doesn't matter what the password was or even if the email was right for that password. It just returns true for potentially any user, often the first one it finds.
Precisely. It bypasses the password check completely. You can often log in as the first user in the table, potentially an admin, without knowing their password.
That's right. Yeah, incredibly effective for such a simple input. The PDF also mentioned ways attackers deal with limitations, using semicolons and comments.
Right. Just like with command injection, a semicolon can often be used to terminate the intended SQL query and start a new malicious one.
Yeah.
For instance, an attacker might inject drop users.
Drop users. That would just delete the whole user table.
Exactly. And at the end is crucial. That's a comment marker in many SQL dialects, like MySQL. PostgreSQL often uses hashtag comment, also works. It tells the database to ignore the rest of the original query.
Like the closing quote or other bits that would otherwise cause a syntax error.
Right. It lets their malicious drop users command execute cleanly. Now, the PDF does note that some database systems might restrict executing multiple statements like this in one go.
A potential hurdle, but maybe not a complete stop.
Often not. And then there's the union attack, which the PDF also detailed. This one's really powerful for stealing data.
Union. That SQL keyword lets you combine results from different select statements, doesn't it?
It does. An attacker exploits this by crafting their input to append a union select statement onto the original query. This lets them pull data from other tables they're not supposed to see.
How does that work in practice?
Let's say the original query was meant to fetch, say, a product name and price, 2 columns. The attacker might inject something that turns the query into select name, price from products, where it'd a union select username, password from users.
Whoa, so if the original query returns results, the database will also run select username, password from users, and stick those results onto the end.
Exactly. But there's a catch, which relates to mock exam question 2. The number of columns in the union select must match the number of columns in the original select.
So in my example, if the original selected 2 columns, name, price, the injected part also needed 2, username, password. What if they only wanted one piece of data, like just the password?
Then they'd have to select something else, maybe even a dummy value or the same column twice, to make the column counts match, like the mock exam answer. Union select password, password from users, selecting the password twice just to match the expected 2 columns.
Okay, so they can essentially tack their own data retrieval onto the application's legitimate query. But how do they know what tables or columns even exist to query them?
Good question. The PDF explains they can often query the database's own metadata. In systems like MySQL, there are special tables like informationschema.tables and informationschema.columns.
Like a built-in directory of the database's own structure?
Precisely. By injecting queries aimed at information schema, like union select table name, null from information schema.tables, adjusting column counts as needed, they can list out all the tables. Then they do the same for columns in interesting tables. It's reconnaissance.
Mapping out the target before extracting the loot. And mock exam question 1 pointed out that even just seeing a database error message after putting a single quote in a URL parameter can be a big clue.
Yes, absolutely. If you put a character, like a single quote, into a URL or form field and the page blows up with a database syntax error, that's a very strong sign that your input is being jammed directly into a SQL query without proper handling. It screams potential SQL injection vulnerability here.
It doesn't guarantee it's exploitable, but it's a huge red flag.
Definitely warrants investigation.
So thinking about the CIA Triad again, confidentiality, integrity, availability, SQL injection seems to hit confidentiality hard, letting attackers steal data.
For sure. But also integrity, right? If they can inject update or delete commands or even drop table.
True. They could change grades, modify financial records, delete users, and I suppose if they messed up the data badly enough, it could even affect availability if the application stops working correctly.
It certainly could. So again, how do we defend against this? Both the lecture and the PDF were pretty clear on the best approach.
And that is?
Prepared statements. Also known as parameterized queries. This is the gold standard, heavily emphasized in the Web Security Lecture 1.pdf.
Prepared statements. Let's break that down. How do they stop the injection?
Okay, so instead of building one big SQL string with user data mashed into it, you first send the structure of the query to the database using placeholders, often question marks, where the user data will go.
Like a template. Select name, grade from, users where email lists, and password again.
Exactly. Then, in a separate step, you provide the actual user input, the email address, the password attempt, to the database driver, telling it these are the values for the placeholders.
And the key difference is?
The database engine knows that the values you provide in that second step are just data. They were never treated as executable SQL code. The structure of the query is already fixed. The input just fills in the blanks as literal values.
So if someone enters ORR11 as a password,
the database just looks for a user whose password is literally the string ORR11. It doesn't interpret the ORR or the 11 as a logic. It treats the entire input as the password data to compare against.
That completely neutralizes the attack. The PDF had examples in Python and Java showing this right, contrasting the dangerous string building with the safe prepared statement way.
Yes, clear examples using things like cursor.execute with parameters in Python, or prepared statement.setString in Java. That separation of code and data is the crucial element.
Now, what about input sanitization? Like trying to escape or remove dangerous characters like single quotes? Both sources mentioned it.
They did, but primarily to caution against relying on it manually. The PDF in particular strongly advises against trying to write your own sanitization logic.
Why? Seems like a logical approach.
Because it's incredibly difficult to get right. You have to account for all sorts of weird character encodings, different database contexts, subtle edge cases. It's notoriously error-prone. You're almost guaranteed to miss something, leaving a vulnerability. Prepared statements handle all that complexity correctly and safely behind the scenes.
So don't try to be clever and sanitize it yourself. Just use prepared statements. The data and information lecture also touched on this, saying simple escaping might not be enough, needing context-aware escaping.
Exactly. What might be safe in an HTML context could still be dangerous in SQL, or vice versa. The lecture also warned against things like the old magic quotes feature in PHP. These automatic, often incorrect attempts at escaping just cause more problems. If you absolutely can't use prepared statements in PHP, which is rare and generally bad, you'd use specific database escaping functions right before the query, but prepared statements are still vastly preferred.
Okay. So across both command injection and SQL injection, the big lesson seems to be never ever treat data that came from a user as if it were code you wrote yourself.
That's the absolute heart of it, and it follows that a lack of proper input validation is the root cause of so many of these issues. Assume all external input is potentially hostile until proven otherwise.
And validate it early, right? Both sources stress doing it right when the data enters the system at defined checkpoints.
Yes, validate early, validate often. And remember, the preference for whitelisting, defining what's allowed over blacklisting, trying to guess what's forbidden. Whitelisting is fundamentally more secure.
Beyond these specific injection types, what were some of the broader security takeaways that apply more generally?
We'll definitely learn the common pitfalls for your specific language and platform, know which functions are inherently risky, like those system or exec type calls, if used improperly.
And don't reinvent the wheel. Use trusted libraries for things like validation.
Absolutely. Leverage existing, well-vetted security libraries instead of ruling your own. Defense in depth was another key idea. Use multiple layers of security. No single fix is perfect.
Testing is important too, right? Trying weird inputs, fuzzing.
Yeah, actively try to break your own application with unexpected data. Use static analysis tools to scan code for potential issues, maybe runtime analysis like tainting to track how untrusted data flows. And of course, rigorous code reviews are essential.
Having another pair of eyes, specifically looking for security flaws. And those resources, like the OWASP Top 10, kept coming up.
They're invaluable because they show what attackers are actually exploiting in the wild. And you see injection right up there, along with things like cross-site scripting, XSS, which also involves mishandling user input, often in an HTML context. Many of the top risks trace back to input validation.
So it's really about shifting your mindset during development, thinking defensively from the start.
Precisely.
Mm-hmm.
Security shouldn't be an afterthought you try to sprinkle on at the end. It needs to be baked in, thinking about minimizing the attack surface and handling untrusted data safely right from the design phase.
This has been incredibly insightful. It really highlights just how fundamental secure handling of user input is. It's not some obscure corner of security. It's right at the foundation.
Absolutely. And understanding these concepts isn't just for security specialists.
Hmm.
Anyone building or even just using software needs to appreciate these risks.
That leads perfectly into a final thought for you, our listener. Given this increasing interconnectedness of everything, what do you think are the shared responsibilities between the developers building these systems and us, the users interacting with them? How do we collectively ensure the security and integrity of our digital world?
That's a great question to ponder. There's definitely a role for everyone.
Definitely something to think about. If you want to learn more, do check out resources like the OWASP Top 10. Thank you so much for joining us on this deep dive.